All right. So, guys, here's where we're at. I want to give you the goals for today, if you will, because, guys, we're going to. Today's a good day. We're going to accomplish a lot. So, guys, this is our goal for today. 2 goals. One is the lab that you have in front of you just became a rough draft. Guys, these are not due today. I told you that before. What we're going to do is we are going to walk in here on Friday with your final drafts. And guys, on Friday, when you go to turn in your final drafts, you should have this strangely satisfying experience when you put a staple in that and you're like, this is really good work. Guys, you're going to have that experience on Friday, because we are so going to dial these labs today that this is going to be something you really can, sounds weird, take some pride in. So guys, that's goal number 1. Guys, goal number 2 is this. And I don't say this boastfully, but guys, I write really well. It's one of the things that I do well. And if you think it's not okay to talk like that, guys, you got to understand that's kind of what life and education is about, is figuring out what you do well, but also figuring out what you can't do. And guys, one of the things I do well is I write. And I learned to write well in high school. But guys, I did not learn to write from my English teachers. I know that my English teachers developed some skills, but guys, the person that taught me to write well was our humanities teacher. His name was Mr. Otto. And I had him all 4 years of high school. And this man drilled into me the skills to make me a good writer. And guys, it served me for the rest of my life. So guys, we're going to talk about that today. My intent here is not to make you a great writer in a day. But guys, my intent is to help you write better than you could have 20 minutes ago. So guys, we're not only going to talk about what the answers are to these conclusion questions, we're going to talk about how to answer these questions well. We're going to talk about how to parse questions. We're going to talk about how to write towards an audience. And we're going to talk about how to write well. So guys, for some of you, you're going to find that maybe even more meaningful than what we do with chemistry. So guys, this is how we're going to do this. We are going to allow the conclusion questions to drive the conversation. We're going to answer these conclusion questions one at a time. You're going to be editing like mad as you're working on these conclusion questions. We're going to get your graphs tightened up. And guys, when you walk out of here today, you're going to have everything you need to, over the next couple nights, really get these labs dialed in. Now, if at the end of this you still think your lab is money and you want to turn it in, that's great. But I've never had anybody do it. As a matter of fact, in the last 3 class periods, nobody's made it past question number 1. You ready? Here we go. Where's my laser? All right, so guys, join me if you would, please, on question number 1. Guys, read the question. It's on, you have it on your paper, but you can join me on the screen. Guys, the question says this. On a molecular level, what effect does the addition or removal of energy have on the molecules of a substance? So guys, here's what I want you to do. Read your answers to yourself. Read your answers. Just in your head, read your answer. Just refamiliarize yourself with what you wrote. Melanie, you're skipping ahead. You guys done reading your own answers? Now, guys, quietly read them to each other and learn from what the other person wrote. Go. Guys, you got about 10 seconds. Merrick, if I can interrupt, did you say on the other hand? That's brilliant. I love that. Guys, what you're going to find out is that one of the really great skills that you can develop as a writer is tricking your reader into caring about what they don't otherwise care about, right? And little phrases like on the other hand are seriously like bait to your reader. They're going, wait, on the other hand, what was the first other, wait, where, over. Guys, that is really the trick to being a good writer, is tricking your reader into caring. Things like on the other hand are brilliant ways to do that. But let's get into this. All right, so guys, it goes like this. The answer to question number 1, you never directly learned from me. We have flirted with this idea. We've talked around this idea, but we ain't never really said it. But I'm guessing that a lot of you know it. So guys, what we're going to do is we are going to talk about on a molecular level. So guys, on this level, when we add energy to the water molecules, what do? They move faster. They speed up. Now, guys, imagine that this was wax. If this was wax and if we removed energy from it, what do? What do? They slow down, right? So, guys, if you're not sure how we know that, let's talk about it. Look at your graphs. So guys, if you look at, well, let's just do it with hands. Guys, when you add energy to the water, the temperature goes up, right? But guys, understand the answer to that, and when the wax, the temperature goes down. But understand, on a molecular level, the answer is not temperature. Temperature is evidence of speed change, but on a molecular level, the speed is changing. But now, guys, let's take this concept and let's turn it into an intelligent sentence. Now, guys, or maybe sentences. Guys, look at your answer. If you rewrote the question in your answer, you already know that you did this wrong. Because, guys, if you are writing well, it's unnecessary to rewrite the question. Why? Because when you're writing well, you are generous with your reader and you introduce the reader into what you're thinking about. So guys, the way to, and I know people say restate the question. That's really not what you're doing. You're bringing the reader into the thought. So if you're going to talk to the reader about what effect the addition or removal of energy has, that's where you start. The addition or removal of energy can cause ... Cause and effect, right? Now, guys, as you're doing this, please, my goal in this is not to have 25 versions of the same words. You need to find a way to make this yours. But, guys, when you are answering questions, you invite the reader into the thought, and in this case, you do that by bringing them to what you're thinking about. Hey, I'm thinking about the addition or removal of energy, and as I think about that, here's what's going on a molecular level. Do you understand the idea? Okay, so guys, with that said, where does the thought go? If we add energy, what happens to the molecules? Faster. If we remove energy, what happens to the molecules? Slower. So, guys, in the end, it's speed. Now, guys, understand there's two ways, just a second. There's two ways that you could have approached this. You could have said an addition of energy makes them go faster, period. The removal of energy makes them go slower, period. And that's fine. But guys, understand you can also group these together in one overarching idea that the addition or removal of energy changes the speed. Go ahead.
Could you also add in there, I
Mm-hmm.
I said like addition energy causes molecules to separate, or like removal energy causes them to condense. Would that be true?
It is true, but you also need to mention speed.
Okay, so if I add speed to it, it's the true answer.
Sit tight for 3 minutes. Okay, yeah, but you're not wrong. I think we just need to recraft it a little bit, especially condense. Okay. So guys, are we sitting okay? Okay, now guys, and this is important. Once you have crafted an answer to the question, you now need to make sure that this answer really makes sense. So guys, join me here for a minute, and let's remember what we did in the lab last time. So guys, you ready? Now we actually have some water, but we know it looks like this, right? So inside of here, guys, we put the Bunsen burner underneath the water, and what did we see happening? Temperature went up, right? We can't see the molecules. All that we have is temperature data. But guys, what does the temperature tell us is happening to these molecules? They're moving faster. Guys, really a thermometer is a molecular speed gun. It's telling you how fast the molecules are moving. So guys, now let's replay the lab in our minds. So time 0, write it down, start the stopwatch. Every 30 seconds, what's happening to the temperature? It's going up and up and up and up and up, right? And then guys, at some point in the lab, the water started to boil. And when the water started to boil, the temperature stopped changing because we took the Bunsen burner away, and then the temperature just stayed at the same temperature the whole time it boiled, right? You had to. No, you did. Because guys, if you didn't take away the Bunsen burner, the temperature had to keep going up, right? Because we said adding energy changes the speed, which is temperature. So guys, if the temperature stopped going up, you must have taken the burner away, right? No. What that means is our answer is not complete. So guys, we're right that adding energy can cause the speed to change the temperature. But that's not the complete answer. Guys, when the temperature stopped changing, on both of your graphs, boiling and freezing, when the temperature stopped changing, what was changing? The phase. Your liquid was becoming a gas. Your liquid was becoming a solid with the wax. So guys, the complete answer is this. It can also change the phase. And Melanie, that's what you were sort of getting at, right? Yeah. So guys, we now have a complete thought to question number 1. Again, we invite our reader in. The addition or removal of energy can. And then we need to mention that it can either change the speed, not temperature, the speed, which we see as temperature, or it can change the phase. You've got to mention both. You could go energy up, energy down, speed down. That's fine. But you need to talk about speed and phase. Now guys, while we're at it, and I wouldn't have expected you to know this on your own, but while we're talking, we may as well make this fully complete. Guys, did you know this? The temperature and phase cannot change at the same time. If something is boiling, its temperature can't change. And if its temperature is changing, it's not boiling. And guys, when something freezes, its temperature does not change. Yours did a little bit because the wax is impure. We'll talk more about that in a minute. But guys, that then provides the complete answer to question 1. So gang, let me sort of sit tight for a second here, give you a moment to gather your thoughts. Certainly questions if you would like. Yeah. It would just keep going down. Eventually it would reach the temperature of the ice water. We call that thermal equilibrium. Eventually it would, because remember it was the ice water that was where the heat was going. And so eventually it would reach thermal equilibrium with the ice water and it would stop dropping. Yeah.
With the not changing at the same time.
Yeah.
The thermometer is a general measurement of the whole substance, not from what each one.
It's an average.
Like,
It's measuring an average.
Not every molecule is rising temperature at the same time.
They are all rising, but they're not rising. It's not like they go, all of them go 21, 22. It's an average. Yeah. Yeah, and actually it's way more interesting than that. The way the average distributes over the sample, it's really cool. We talk about it in AP. How we doing, y'all? You ready for this? Are any of you still going to turn in your lab? And we didn't even make it through question 1, right? But
My question one, I just know my question 2 and 3 are
there you go. That's fair.
gonna be fine.
All right, guys, do we need any more time with question number 1? All right, then let's do this. Ready? Question number 2 reads like this. Read the question with me. So, guys, it says, look at your graphs and summarize the temperature trends you observe over the boiling and freezing point curves. Stop. Guys, before you do anything relative to this question, let me ask you a question. What is this question asking you to do? Think about it. What is this question asking you to do? And as a result, what does an appropriate answer to the question look like? So guys, when you answer this question, you're looking for verbs. There are 2 verbs that this question is asking you to engage in. The first one is the very first word, which is what? Look. What are we going to look at? Our graphs. But guys, here's why that's important. You need to invite your reader into the looking. And we'll talk more about that in a minute. But then guys, once you've looked, what's the next verb? What is this asking you to do? Summarize. So guys, when we talk about summaries, we're talking about general observations. But guys, what are we summarizing? Temperature trends. So guys, now with this in mind, let's go look at our graphs. So guys, grab your boiling point graph. Now, imagine this. Imagine that I had never seen the graph that is behind me, and imagine if your challenge was to get me to draw that without looking at it. What would you tell me to do? Where would I start? Bottom left corner. Then what would I do? What would my line look like? Diagonal up to the right, and then what? And then it would go horizontal. That's a summary. Up and not up, right? But now, guys, you have got to turn that into something that your reader can access. So invite them in on the journey. How do you do that? Looking at the boiling graph, or on the boiling graph, or referring to the boiling graph. But guys, you got to take your reader with you. So the beginning of your answer to this question is going to bring you and the reader into the graph you want them to look at. So you're going to start with looking at the boiling graph. Now you've got to step them through time. So guys, what kind of words do we use to step people through time? We use words like at first or initially. Adverbs, guys, money. If you can huck an adverb in there, you won the battle. My favorite adverb, by the way, guys, interestingly. Oh man, that is the most manipulative word in writing. Because if you write interestingly, comma, and then keep going, you just suckered your reader in because they're going, wait, what's interesting? Squirrel. And they start chasing you around. Guys, man, I tell you what, your goal for the rest of your academic career is to use the word interestingly in every paper you write. Change your life. You might be surprised. Yeah? Yeah. Yeah. Yeah, I mean, you could get into the temperature went up in a linear fashion. We just need to know it went up. Yeah. So guys, just a second, Luke. So maybe we say this. At first, the temperature went up. That's a trend. Then period, what happened next? Leveled off. So we could go on the boiling point graph. At first, the temperature went up. Period. Then it leveled off. Period. You're done. Right? What is? Plateaued. Ooh, that's got a lot of vowels in it. A's and E's and Did you say asymptote? Well, technically. So technically an asymptote is a point where change goes to 0. All right. Just don't spell it wrong. All right. So now guys, do this. Take your developing ability to answer questions and apply it to the other graph. And by the way, guys, let's join me for just one moment, please. So, guys, I talked with you about this as I went around, but let's talk. This is what should have happened. But most of your graphs kind of went down and then down less and then down again. Guys, the freezing should be a plateau. The reason that it wasn't is your wax was impure. And the more impurities you have in your wax, the more the freezing would have sloped. It's actually a way in college you measure purity. You freeze your products, and if they don't freeze at one temperature, if they don't plateau, you know you have impurities. But that's what happened if it didn't plateau. But let's talk about it like it went down, didn't go down, and went down again. So now, guys, what are you going to say for the rest of question 2? Go for it. Hallie, is this working? Like trying to edit on there? Is it working? It's what? Huh. That's interesting. I'm just, wheels are spinning, right? I wonder if this would be a better way to do this next year, because everyone has Chromebooks. Yeah? My concern, and I want to talk with you more about this. My concern would be that you're now so focused on getting exactly the right words that you're not really editing. You're creating your final product. Do you know what I mean? Yeah, you're changing, but I think a lot of people that are writing on paper are going, oh, I need to include this, but they're not figuring out exactly how to craft it. Do you know what I'm saying? Oh, you could use comments, yeah. All right, guys, so can we talk about this? So how many trends do we need to talk about on this graph? So, guys, what we're going to do then is some form of this, right? Now, referencing the freezing graph. At first, the temperature went down, period. Then, depending on your graph, you'd say then it went down less rapidly. If it really did, you could say then it stopped changing. But something about the rate, the slope decrease. Can we even do math together? But the change was less rapid, and then it started changing again more rapidly. But again, guys, 3 regions there, right?
So we should include specific things in here, like I had like the first, like within 30 seconds.
Yeah, no, that's totally fine. Absolutely, you can do that. I've had people that have said, like on the boiling point graph, at 96 degrees, it stopped changing. Those are fine. You don't want to get into such detail that you're no longer summarizing, but I don't think you're flirting with that line. Oh, shoot. Don't push that button. All right, guys, are we okay? Are you feeling good about question 2? Good? Okay, then this, guys. Go to your boiling point graph. Go there with me. And now let's edit our graphs. So, guys, looking at your graph, this is what we're looking for. When I say we, I mean me and Miss Collin, the grading rubric we put together. So, guys, first of all, you need a title. The title needs to simply describe what the graph is about. So you can't just put boiling, or boil. It's boiling of water or something like that. So what does this represent? The boiling of water. Then guys, you need units, not units, but labels on both axes. This is temperature in Celsius. This is energy. But it's actually time units, right? But guys, water doesn't get hotter as it gets older, right? So if this was time and temperature, there would be no graph. Water doesn't get hotter as it gets older. What we're really doing is adding energy over time. And so guys, we're just going to label this energy even though we graph time units. You can just call it time intervals. That's the point. We don't. The only way to really measure it is by knowing how much gas we burned. But even at that, it's not accurate because a lot of it goes into the room. Then, guys, this evenly spaced units. Looking at your graphs, they were all landscape. They were all good in terms of being more than half the page. Then, gang, you need your points. And you need lines connecting them. And then, gang, this was not a requirement initially, but let's do it now. This, in this region, if you will, this is a liquid. And then in this region, it's boiling. Guys, please label them simply so that we can use those references when we talk about this for question 3. So, guys, do you need any more time with perfecting this graph? Y'all good? Okay, so, please. Oh, hey guys, just so you know, all of this is graph paper and it is always freely available to you. Take all you need. It's always right there. Okay, so then gang, oh shoot. Go by. We're okay. We're okay. We're fine. All right, so then, gang, similarly with your freezing point graphs, title, units, labels, and then if you would please, here we have a liquid, it's freezing, and then it becomes a solid. So if you would include those labels as well. When the temperature stops changing or changes less rapidly. So guys, give your graphs, your freezing graphs a once over. And then guys, we've got about 30 minutes left and we've got one more conclusion question to answer. We're doing great for time. Remember, it's early out. You guys okay on question 2 and your graphs? Anybody need more time? Carter's still working away, which is great. By the way, guys, if you get home and you're like, shoot, what did we need on our graphs? Remember, it is on the handout, but there's also the screencast. You guys okay? Good. All right, y'all. Question number 3. All right, guys, question number 3. My hope is this. My hope, guys, is that over the last 20 or 30 minutes, at some level, you've developed some new strategies for approaching and answering questions. Interesting. Guys, do any of your English teachers talk with you about the things we're talking about? No. Isn't that interesting? But guys, it doesn't mean that our English department is deficient. Right? They are about the skills of writing. But guys, I would propose to you that really it's in your other classes where you can take those tools and actually start swinging them as tools. And that's what we're doing now. In the same way that my history teacher taught me how to use these tools, maybe we're doing some of that. So guys, do this. Reading question number 3. It just says this: on a molecular level, what are possible explanations for these trends? So guys, let's think about 2 things. What are the verbs? What are you being asked to do? And then guys, number 2, how do you invite your reader into the conversation? Talk about it. interestingly.
Water boil at a different temperature if it's impure.
It does. That's what we're going to talk about on Tuesday.
So
Yeah.
so our because we're above sea level.
Correct. The problem is actually with your thermometer. These thermometers are not zeroed. So they measure change accurately, kind of like the beaker and the salt thing we did, but they don't measure individual temperatures accurately. The very first thing we do in AP chemistry is calibrate our thermometers. Yeah. Okay, guys, you got about 20 seconds left, and then we're going to chat. All right. Hey, so guys, let's chat. Isn't it interesting that we can have conversations not about content, but about how to approach questions? Yeah. So guys, let's talk about how to approach this question. So first of all, let's talk about the verb. What is this question asking us to do? Explain. So now we're going to be explaining things, again, on a molecular level. But guys, this, what are we explaining? The trends. But now we got to be careful because it specifies these trends. And guys, when you see these, your question should be which? Which trends? Yeah, these trends are these trends. So the trends that we are explaining are the trends that we identified in question 2. Now guys, do this. How many trends did we identify in question 2? 5. Goes up, don't go up. Goes down, don't go down, goes down, right? So guys, we have 5 trends. So as we think about that, what might a complete answer to this question look like? 5 sentences, right? If we need to explain 5 things, we're probably going to need 5 sentences. Now, guys, we're going to go a little next level on this, and I'm going to share with you some strategies that might allow you to condense this a little bit. But, guys, fundamentally, we know, are we okay that we need 5 sentences for 5 explanations? Okay, so, guys, let's start picking the fruit. Goes like this. Explain that to me. The temperature is going up. On a molecular level, what's going on? No. What's going on? They're moving faster, right? So, guys, how do we craft that into an audience-sensitive response? On the boiling point graph, as the temperature goes up, the speed's going up. You're like going, duh, kind of already knew that. Guys, how did we already know that? We answered question 1. Didn't we establish that in question number 1? The addition or removal of energy causes the speed to change. There's an example of that. So guys, our first sentence is an explanation of temperature going up because speed is going up. Yes? Can we go on to trend number 2? Speed. Temperature is evidence of that. You guys good? Okay, now guys, trend number 2 is this. The addition or removal of energy can also cause the phase to change. But guys, stop. That is not an explanation at a molecular level. Molecularly, what is going on when it boils? We're going to put that in our back pocket and we're going to talk about it in a minute. So now let's move on to our next set. Let's move on to our next set of trends. So guys, we're going to skip boiling, and now we're going to go over here, and let's talk about this. What explains the fact that the temperature is going down? Go ahead. Go ahead, Jacob. And what does that do to the particles? Slows them down. And guys, what about here? What's going on? Slowing down, right? So on the boiling point curve, when the temperature was going down initially or at first, molecules were slowing down. Then we're going to talk about freezing in a minute, but we can already write that 5th sentence. When the temperature started going down again, the molecules were slowing down again. So guys, we just wrote 3 of our 5 sentences. On the boiling curve, temperature up, speed up. On the freezing point curves, at first, temperature down, speed down. In the end, temperature down, speed down. How are we doing? Guys, you want to take this next level? You don't have to do this. But I would propose to you that you can take those 3 sentences and combine them into one sentence and say the same thing. What do those 3 sentences have in common? Temperature is changing and speed. Up and down, it's still changing temperature, changing speed. So could we say this? On both of the graphs, anytime the temperature is changing, the speed is changing. That summarizes all 3 of those trends in one sentence. And that one sentence sounds surprisingly like the first sentence that we wrote in the first question. Huh? There's a method to our madness. But guys, again, it's up to you. If you like the 3-sentence structure, temperature up, boiling graph, temperature up, speed up, freezing point, temperature down, speed down, temperature down, that's fine. Oh, yeah. Man, I tell you what, guys, that for many of you, if you get into the sciences, it's going to be the hardest thing for you to do. And frankly, another reason to come and take AP from me next year. Guys, one of the hardest struggles, let me say that differently. One of the things that my students in AP Chem benefit from the most is learning to write in an academic setting. Do you guys know Ami? Do you know her? Like, seriously, like, there are times that Ami wants to punch me. Because I'm like, Ami, stop. She just writes forever and ever. And I'm like, you get 3 sentences. You go more than that, and I'm going to kick you. Because she is really good at writing in an English context, but darn it, girl, you got to dial this back and learn to pick your words. And so it's getting better. Love that kid. But, guys, understand that writing in a scientific context is a whole other beast. It really, really is. So, guys, are we good on up and down and down? You okay? So do you understand what we have left to do? Guys, we've got to talk about freezing and we've got to talk about boiling, yes? Say yes. Hey, there we go. So guys, we're going to do this differently. The last thing that you need right now is another piece of paper on your desk. Guess what I have for you? Another piece of paper for your desk. I know. Yeah, thanks for nothing. All right. You bet. We'll talk about it at the end, but we're going to put together a final packet of 5. Okay, so guys, this is where we are. Here's what we've got left to do. Guys, we need to talk about at a molecular level what is going on when this boils. We know the phase is changing, but at a molecular level, what is going on? Then we got to go over here, and we know that this is freezing, but at a molecular level, what is going on? Now, guys, here's how we're going to approach the question. We're going to be detectives. Grab this paper. So, guys, what does this paper have to do with conclusion question number 3? Guys, be ready to write all over this thing. So, guys, this is a solid. You already have this on your paper. This is a liquid, and this is a gas. So now, guys, watch. We already know that when we heat up a liquid, don't write this down. When we heat up a liquid, the temperature goes up. When we cool down a liquid, the temperature goes down. The molecules are moving faster and slower. Question is this: what's going on when it boils? And what's going on when it freezes? When a liquid turns to a gas, what's going on? When a liquid turns into a solid, what's going on? So guys, here's what we're going to do. We need to figure out these spaces. When a liquid becomes a solid and a liquid becomes a gas. But to do that, what we're going to do is we're going to talk about what are solids like, what are liquids like, what are gases like. And if we know what they're like, and if we can compare them, we know what's changing when they turn into the others. Do you understand the logic? So guys, let's fill this out. So let's start in the spaces. So guys, I think you know these things, but let's be sure. So guys, when a solid turns into a liquid, the highly technical term for that, I don't know why this is doing this. Guys, the technical term for that is melting. I know. And then guys, conversely, when a liquid turns into a solid, we call that freezing. But guys, this is strange. Some of you are old enough to vote, and you're not going to know the answer to this question. You ready? What, and Fahrenheit, bad, right? Water freezes at 32 Fahrenheit, bad. Guys, what temperature does water freeze at in Celsius? Zero. But what about this? What temperature does ice melt at? Also zero. Guys, water freezes and melts at the same temperature. So now let's go over here. When a liquid becomes a gas, of course, we call that boiling. No. But guys, what about the other direction? What do we call it when a gas becomes a liquid? Do you know? It's called condensing. Condensation is the noun. But yeah, it's condensing. And guys, 212 Fahrenheit, right? Water boils at 212. What does it boil at in Celsius? 100. But guys, do you know that it's actually physically impossible to get water to 100 degrees Celsius in Utah? It's an altitude thing. We're going to talk more about that later. But guys, fundamentally, right now you need to know water in Utah boils at about 96. We'll talk more about why later. By the way, if your water got above 96 degrees, like your guys has got above 100, right? It's because your thermometer's tweaked. It's not because you actually got water to 100. All right, so guys, here we go. What we're going to do now is we are going to dig into what these things are like. What are solids like? What are liquids like? What are gases like? You have lines to write these down, so do this with me. Here we go. So guys, first of all, solids. Guys, solids are low energy systems. When you think about a solid, think about ice. And guys, what is ice doing? Well, this doesn't have a bunch of energy. So it's just sitting there and vibrating. Guys, these things are all packed together. They have high densities, and they just sit there and vibrate. They're all locked together, intermolecular forces, and they just sit there and vibrate. We're going to talk in a second. So guys, looking at this representation of ice, let's be clear. What do the purple sticks represent? What locks them together? Intermolecular forces. So they're all locked together with intermolecular forces, and they just sit there and wiggle. Can you make them wiggle faster? Yeah, heat them up. Can you make them wiggle slower? Cool them down. Do they ever stop wiggling? No. We've been within 1/10,000,000th of a degree. What do we call the temperature where they would stop wiggling? Absolute zero. But we've never been there, and we never will. So, guys, with that said, solids have fixed positions. Their particles cannot move around. As a result, solids can't sock. No sock. No sock. No sock. Well, it's a fine question. You ready for life-changing science? Here we go. Guys, this is a solid. What shape is it? A cube. What about now? Hey! Guys, solids do not take on the shapes of their containers. Suck. So guys, why is all of this true? And fundamentally the answer, guys, is because solids have very tightly bound intermolecular forces and high levels of structure. Well, it does get better though. Don't be disappointed yet. Just wait. Careful. So now, guys, this. Let's take our solid and let's add some more energy to it. So guys, check this out. As we add energy to the solid, it vibrates faster and faster and faster and faster and faster and faster and faster, and eventually like a eventually like a building in an earthquake, this thing collapses and it turns into a liquid. Okay, so guys, when we talk about liquids, these have mid-densities. And guys, what is it like inside of a liquid? If solids are sitting here vibrating inside of a liquid, guys, it's a mosh pit. Melanie will tell you from living in Wyoming, you don't want to be in a mosh pit in Wyoming. People will hit you with beer bottles. Never mind. I just recorded that. That's bad. Scratch that. But guys, no, seriously, if you've ever been in a mosh pit, you know how crazy it is. You're slamming into each other. You're getting just abused from all directions. The song stops. You have no idea where your friends are. It's chaos. Guys, that is what it looks like inside of a liquid. It is full-on chaos. Guys, as a result, these molecules have random positions. And as a result, Bree, you ready? Wait for it. They toe sock. Oh. All right, guys, ready for some more life-changing science? Toe sock. What shape is the water? Beaker shaped. What shape is it now? Flask shape. Okay, you get the idea. So guys, what are liquids all about? Well, guys, liquids still have intermolecular forces, but they do not have structure. No structure. Although the thing that's interesting, and I don't want to talk about this more than just a blurb, up at the University of Utah, they're actually finding out that water does have structure. Liquid water has structure. I mean, the research up there is, they found a new way to conceptualize water, and they're finding structure in liquid water. It's fascinating. I mean, Nobel Prize perhaps winning research on water. It's really crazy. All right, so now guys, let's do this. Ready? We're going to take our liquid and we're going to add even more energy. You ready to go? So guys, we got our liquid and we add energy and they move faster and faster and faster. And I'm not going to do it, but eventually they end up flying out of the top, right? And guys, as they do this, their density goes way down and these particles are just flying in straight lines. They run into each other. They run into the walls. But guys, they're moving in straight lines. Of course, they have random positions. But guys, this is also true. Gases not only toe sock, they tozvok. All right, you ready? So guys, here's the deal. Liquids and gases both take on the shapes of their containers, but they do it differently. What does the gas do that the liquid doesn't? Fill the entire volume. That's your V. So guys, gases fill the entire volume and not just the shape. The liquid only fills the part of the container that it can. Gases spread out and fill the whole thing. Why? They ain't got no IMFs. All right. So guys, we are now ready to complete our labs. This is the last step. And it goes like this. Guys, we have already established that when we add energy to a liquid, the molecules move more quickly. That was the first part of question 3. But now, guys, we're ready to figure this out. We are still adding energy, and them molecules ain't moving no faster. But if we're adding energy, something has to be changing. Guys, what is the thing that, don't say phase, molecularly, what is the thing that is changing when a liquid becomes a gas? Jacob. Let's do liquid to gas. So when a liquid becomes a gas, what's changing? Spreading out. And what allows them to spread out? What's breaking? The intermolecular forces. So guys, these have intermolecular forces and these don't. The breaking of the so when you're adding energy to water and that energy is causing that water to boil, the molecules can't move any faster. All the additional energy is ripping the intermolecular forces apart and allowing these to fly out. So guys, now you have that additional answer to question 3. In the boiling curve, when the temperature is not going up, the IMFs are breaking. Good? You okay? So now, guys, what about this? What about, and this is going to freak out, guys, what about the other side of the proverbial coin? So here, with our wax, throw it in ice and it cools down, but then it stops cooling down, and then it cools down again. So guys, now we're saying this. We had hot liquid wax, and we cooled it down, and they slowed down, because then they stopped slowing down. And when they stop slowing down, what's changing as a liquid becomes a solid? It's one word. Talk to the person next to you. What's changing when a liquid becomes a solid? So you ready, guys? What does a solid have that a liquid doesn't? Structure. And guys, that's it. Check it out. You take liquid water or wax and you cool it down, and eventually these guys cannot move past each other. The mosh pit is done. They all hold hands in loving synchronicity. And never mind. But guys, like Sunday in Wyoming. And guys, they do this. Stop. They do this, and they all lock together and they form a solid. But guys, understand, while they're locking hands, they are not slowing down. Eventually, they can't move past each other, and they lock together and they become a solid, and then they slow down some more. So guys, that's the complete answer then to question number 3. If the temperature is changing, the speed is changing. In the boiling graph, when the temperature was not changing, the intermolecular forces were breaking. And in the freezing graph, when the temperature wasn't changing, the structure was forming. Do you get the idea? Go ahead.
So when the molecules are slowing down, basically means that the intermolecular forces are getting stronger.
Interestingly, no. Because the molecules inside the liquid and the solid, the strength of intermolecular forces is dependent on polarity, right? And the molecules aren't changing shape. They're all polar. But it's also a function of distance. And the distance between the molecules in a liquid and a solid are pretty much the same. So the IMFs are not becoming stronger. What is happening is that the particles no longer have enough energy to slide past each other, and they form structure. Not because the intermolecular forces are strengthening, but because they can't move past each other. Yeah. Are we doing okay, y'all? Shoot, we have 5 minutes. So guys, let's wrap this up and then we'll call it a day. So guys, do this with me to bring this to a conclusion. Guys, let's summarize what we just said and then we'll be good to go. So guys, can we agree with this? And I would encourage you to write this down. When something freezes, we're creating structure. Does that feel okay? So guys, if we're creating structure when we freeze, what's happening when we melt? We're breaking structure. So guys, melting and freezing are all about structure. Then what about condensing and boiling? When we boil, we're not breaking structure. What are we breaking? Intermolecular forces. So here we're breaking intermolecular forces. And then guys, conversely, when something condenses, we're forming intermolecular forces. So guys, we're done. Let me explain to you then, and Jacob, you asked the question a minute ago. Guys, what does this then look like? So on Friday, when you come in, here's what you're going to do. You're going to grab your cover sheet, whether it's stamped or not. You're going to grab your data chart. You're going to grab your 2 graphs. And then, guys, your final print of your conclusions. I don't want your rough drafts. You're going to take all 5 of those papers, put a staple in it, turn those in, and we're done. But guys, that's not where this stops. As I mentioned to you before, not only did we learn science, we learned writing. So guys, there's a homework assignment associated with today. If you're thinking that's a lot to do, it shouldn't be, because your graph should be perfect and your conclusions should only need minor edits. So guys, there is a homework assignment incorporated with today. It's assignment number 4. It is double-sided. Guys, be careful. In order to do assignment number 4 well, you're going to need to take some of the skills that we developed today about writing to questions and apply those on assignment 4. So guys, we will do assignment number 4 as well on Friday. And then guys, we're going back to lab. So gang, we have a couple, oh, you're fine, go ahead. We have a couple minutes left, settle in, and go when the bell rings. Hey.
So I guess I put it with the graph, like diag group as flat, diag flat. So I can understand it defines and as you melt it goes flat. And you don't increase again, but as it boils, it goes flat. What about
Oh, go ahead, what?
gas? Like
Come here.
increase.
Yeah. So, the thing, here, just come and stand with me. Chemistry, general chemistry, we'll just go last year. This material. No, we're not teaching this anymore, but this is what we used to do. So if you take this graph, right, this is our freezing graph. So as time goes on, temperature is going down, energy is going down, right? If we take this graph and flip it over, now we're going to say that energy is going up and temperature is going up. So this is no longer a freezing graph. This is actually now a melting graph, okay? So solid, melting, liquid. And if we move this down and bring in your boiling graph, now we've got the whole picture, which is what you were talking about. So we go solid, melt it, liquid, boil it. But actually what happens then is if we could capture that steam, we could continue to heat it. Yeah, and so that's the idea. Yeah, so the question is what happens next, right? And so the thing that happens next, if you get enough energy into that, you form a plasma. And so what happens is you add so much energy, the electrons strip off the molecules, off the atoms, and you end up with a plasma. Then if you keep going, you get into all sorts of other exotic forms of matter.
So what about the fact that air doesn't, feel especially hot or
Oh, shoot. Oh, thank you.